Okay guys, we're going to talk about Unit 7, SAS1, Euler paths and circuits. Here we had the Königsberg Bridge problem. We did this problem outside to try to get an idea of what we'll be doing for this assignment. Remember, the concept is we want to use each edge exactly one time. So we take this picture and we take the concept and we look at the eastern and western gardens that we were given on page 1 of our assignment. Here we notice what is a vertex and what is an edge. This is an edge and this is a vertex. And so what we want to see is, can we go across each edge exactly one time in the western garden? And the answer is absolutely not. Because we have this vertex, and this vertex that have just a single pathway to them. And making it to one of those vertices means we're going to have to cross that edge twice if we're going to go back throughout the graph. So we cannot use each edge exactly once in the western garden. So let's take a look at the eastern garden. Can we use each edge exactly one time? And I believe that the answer here is yes. Let me see if I can demonstrate here how to do this. I think, let's say we start right there, go around the outside, and then we used each edge exactly once. We started here and ended here. So that's basically the concept. But now we have to take a look at how can we turn some real-world problems into networks of graphs with vertices and edges. So when Leonhard Euler turned his attention to the bridge problem of Königsberg, he turned that problem into this graph. Now, I know that this graph doesn't quite look like the graph we drew outside, but it basically represents everything that is necessary for the problem. Let's take a look. Here's the original problem. If this picture was converted to a graph of vertices and edges, it would look like this, where each vertex represents a piece of land of the city, and each edge represents one of the bridges in the picture. So one of the things that you'll have to do pretty soon is you will have to convert a real-world picture into a graph of vertices and edges. So now let's look at your actual assignment. Questions 3 through 11. The bridge problem is stated: given a problem, find a path through the vertices that uses every edge exactly once. It uses every edge exactly once. That's called an Euler path. If an Euler path begins and ends at the same vertex, that is called an Euler circuit. So I know this is not necessarily familiar to you guys, but these are definitions that you're going to need to be successful in this unit. So question 3. For the following graphs, decide which have Euler circuits and which do not. Remember, a circuit begins and ends at the same vertex. So on graph number 1, if we start right here, we can traverse each edge exactly once, and we end at the same vertex that we began. Graph number 2. You can try this thing several ways, but we started here and ended here. This graph number 1, the answer to graph number 1 is yes, it is a circuit, The answer to graph number 2 is no, it is not. Let's take a look at graph number 3. Let's say we begin right here. So if we take these edges and go throughout this graph, we end and begin at the same place. So the answer to graph number 3 is yes, it is a circuit. And then let's take graph number 4. Say we start there. We'll end there. The answer to graph 4, no, it is not a circuit. So we can clearly tell here that if we paid attention to the definition, we can see that graphs 1 and 3 are Euler circuits and graphs 2 and 4 are Euler paths, but not Euler circuits. So question 3 says which ones are circuits and which ones are not. So graph 1 and graph 3 are the graphs that we need to identify as circuits. Question 4 says the degree of each vertex is the number of edges that meets at that vertex. So we'll look at all 4 graphs and we'll identify how many edges meet at each vertex. So for graph number 1, we have 2 edges that meet there, and you should notice that 2 edges meet at each vertex. Graph number 2. This one has 3 edges. This one has 2. This one has 3. This one has 2. And this one has 2. This is the degree of each vertex based on the number of edges that meet at that vertex. Graph 3. This one has 4. 2, 2, 2, and 4. Graph number 4. 3, 4, 3, 4, 2. So then we take a look at the graphs from question 3 that have Euler circuits and how many have an odd, and how many vertices have an odd degree. So the graphs that were circuits were graphs 1 and 3. How many of those vertices have an odd degree? The answer is none. None of the vertices in this graph or this graph have an odd degree. So maybe there's something to Euler circuits and the degree of each vertex. Maybe all Euler circuits have vertices with an even degree. Maybe, I'm not sure. So for question 6, for the graphs from question 3 that have Euler circuits, how many vertices have an even degree? Well, again, we have the 2 graphs, graph 1 and graph 3, circled. And so how many of these vertices have an even degree? The answer is all of them. All of the vertices in this graph and this graph have an even degree. The number that is their degree is divisible by 2, which is the definition of even. So for question 7, form a conjecture about how you might quickly decide whether a graph has an Euler circuit and explain why your conjecture seems reasonable. Well, our conjecture should seem reasonable based on the answers to questions 3, 4, 5, and 6. We determined which graphs have an Euler circuit, we determined the degree of each vertex, and we found some characteristic that the two Euler circuits had in common. And your conjecture should look something like this. All of the blank of a graph have a blank blank. Then the graph is a Euler circuit. So Euler circuit is what should be last in your conjecture. I'm leaving it up to you to fill in the blanks at the beginning, based on your answers to questions 3, 4, 5, and 6. What does your conjecture tell you about the Königsberg Bridge problem and the garden scenario? Well, here's the Königsberg Bridge problem. If we take a look at the degree of each vertex, this degree is 3. This degree is 3. This degree is 5. And this degree is 3. So if you paid much attention to questions 3, 4, 5, and 6, and you answered the conjecture correctly, you would notice that the Königsberg Bridge problem is not an Euler circuit. Taking a look again at the Western Garden, this degree is 1, this degree is 1, 4, 3, 2, and 1. Taking a look at the degrees, the Western Garden is not an Euler circuit. And then taking a look at the degrees of the Eastern Garden, 2, 4, 3, 4, 2, and 3. The Eastern Garden also is not an Euler circuit, based on the degree of each vertex in the given graph. So for question 9, we got to help Chet, and we got to find him, and we need the most efficient route, which means we want to cover each edge exactly once. This means we have to determine if it's an Euler circuit. And again, we'll know that by checking the degree of each vertex and finding a similar characteristic between the graphs we started with in question 3 and this graph, which looks a little more complicated. And then in question 10, you've been hired to paint the yellow median stripes on a road, and we want to only paint the road and go across the road one time, which means determine if it's an Euler circuit or not. If it is not, explain why. And question 11, determine what situation might it be okay to have a path, be able to get through each edge exactly once, but it doesn't matter where you end and begin. Explain where that might be okay. And this, there will be many answers to it. No one correct or incorrect answer. It's all based on your reasoning. Tell me why it's okay that a path exists and not a circuit. I'm looking for the reason. I'm not looking for the scenario to be the correct scenario. I'm looking for the reason why. Alright guys, I hope I helped you with your assignment today. And I'll see you next class.